All right, now we're going to talk a little bit more about some of the details of working with this normal curve. The first important piece of information about this normal curve is the shape of this curve, the location of the curve, everything that's true about this curve is determined by two values. Mu, the mean of the population, and sigma, the population standard deviation. And here's how that works. For any normal distribution, the curve is symmetric about a vertical line. The center of this normal distribution is always given by mu, the mean of the population. Every normal curve is always centered around mu, the mean of the population is being used to describe. So, if the mean of the population is 50, this is on a number line, this would be centered at 50. If the mean of the population is 80, it would be centered over here at 80. So where this normal curve is located depends upon the value of mu, the population of the mean of the population. The standard deviation works this way. Notice how in this piece of the curve it opens upward, it curves, and so that it opens upward. The word we use in the calculus, we say this is concave, upward. However, in the middle, it opens downward. So see how this opens downward, but this piece of the curve opens upward, and then also opens upward here. The distance between where this changes concavity and the center, since this opens upward, and this opens downward, there must be some point at some position here where this curve changes from opening upward to opening downward. That distance is one standard deviation. Now, another thing that's important to know is this curve is symmetric. The left half and the right half are precise mirror images of each other. And so if this is the distance to the change of concavity on the left, it's also the same distance to the change of concavity on the right. And so the standard deviation sigma indicates how wide this curve is. If the standard deviation is, let's say, 4, let's suppose we're doing a problem where mean is equal to 20 and standard deviation is equal to 4. Then that means this is centered on the number line at 20. But the distance between the center and where this change of concavity occurs is 4 units. And so that value would be 24, the mean, plus 1 standard deviation. That's 20 plus 4 is 24. And then the distance to where this changes concavity on the left is also 4 units. So that position would be 16. That's the mean, 20 minus 1 standard deviation minus 4 is 16. So the center of this curve, where it's located, is determined by mu, the population mean, and the distance between the center and the change of concavity, the width of this curve, how tightly clustered or how loosely dispersed, is determined by the standard deviation. Now, we've talked before about what the standard deviation means. If a population has a relatively large standard deviation, that means the population is relatively loosely dispersed. If the population has a relatively small standard deviation, that means the population tends to be more tightly clustered together. Now, put that together with the fact that the total area under the curve is equal to 1, and there's a consequence of that. And I'm going to draw that picture next. Suppose researcher number 1 is doing research with a population, and let's suppose the mean of that population, let's keep the arithmetic easy. Let's suppose the mean is 40 and the standard deviation is 5. And let's suppose that this is what that picture looks like. So this is centered at 40, and the width of this curve is determined by sigma equals 5. But suppose researcher number 2 is doing work in a different field, and they are also working with a population whose mean is 40. But let's suppose researcher number 2 has a standard deviation of only 2. Now think what that means. The width of this curve is determined by the standard deviation. This is larger than this one, so population number 1 would tend to be a more widely separated population than does population 2. But the key is the total area under the curve must be 1. And so in population number 1, the distance between the center and this change of concavity is 5 units. The distance between the center and the change of concavity is 5 units, but that's for population 1. The distance for population 2 is only 2 units. And so it's still centered at 40, but now it has to change concavity much more closely together. Now what I'm going to draw now is a wrong picture. This is not the correct picture. And there's a reason why we know this cannot be the correct picture. Because population 2 has standard deviation equal to 2, it's more tightly clustered together than is population number 1. That means there tends to be less data further out in both directions. So see how the purple curve is below the white curve here, indicating there's less of the data there. But the total area under both of the curves must be 1. So this is like squeezing a balloon. If you squeeze the balloon on the tails, that air's got to go somewhere. That population has to go somewhere. It's going to come in the center. So this is not the correct picture because there's no way that both of these curves can have total surface area equal to 1. What must instead be the case is something like this. If you lose population in the tails, that means you must gain population in the center, so that the area lost here and here in the tails is exactly counterbalanced by the area you gain in the center. And so a small, narrow, but tall normal curve corresponds to one where the standard deviation is relatively smaller than it is in this scenario. All right, now think. Suppose we now have researcher number 3, and suppose their mean is also 40. But suppose researcher number 3 has standard deviation, let's say their standard deviation is equal to 9. That means this is much more widely dispersed than either of those. There's much more population out in the tails. Well, if you gain population in the tails, if you gain surface area on the ends, that means you must lose surface area in the middle. And so, again, very roughly, very crudely, very approximately drawn, there's more population in the tails, but less population in the center. So one thing we see is there's not just one normal curve. There's a wide variety of normal curves based upon what values for mu and sigma were given, or what values of mu and sigma are used in the population. Now, in each of these scenarios, we have mu equal to 40. Now let's throw another piece into the puzzle. Suppose researcher number 4 still has standard deviation equal to 5. So it's the same as researcher number 1. But now let's suppose researcher number 4 has mu equal to, let's say it's 60. Now think what that means. Do you see it? The mu, the sigma, the mean, the mean of the population tells you where this distribution is to be centered, and then the width is determined by sigma. So is it clear what's going to need to be in this picture is, it's the same width as the original white curve, but we need to pick it up, move it over, put it back in the picture, centered at 60 rather than at 40, and within the limits of my very badly drawn picture, that would be something along those lines where I indicate that the white curve and the blue curve should be the same width, just centered at a different location. What then do you suppose green curve number 5? Suppose we have mu equal to, in this case, let's say 30. And let's suppose the standard deviation is 0.5. It's even smaller than 2. It's a very, very small standard deviation, which means it's very, very tightly clustered. But the center is at 30. So here, if this is, let's say, 30, this has to be a very, very tall, very narrow curve because the standard deviation is only 0.5. Again, my picture may be very bad. But you see the idea, very low probability in the tails, very high probability in the center. Now, these pictures are not drawn to scale, but you get the idea that the total area under each of these curves must be 1 unit. If you gain probability in the tails, that means you must lose probability in the center. If you gain probability in the center, you must lose probability in the tails. And now we have a new problem. Suppose we're interested in finding what is the probability that we obtain an x value, and let's say it's between 40 and 43. So that gives us a new problem to consider. In each of these scenarios, each of these researchers wants to know what is the probability that in my population, or my population, or my population, what is the probability that I obtain a value between 40 and 43. Well, here's 40, here's 43, let's say. So I want to find a value that's in that interval. Now, we talked before, probability is area under the curve. But the problem is we have 5 different curves and 5 different areas to find. In the original white curve, that would correspond to that area. But in the red curve, let's say, the red curve is researcher number 3, the red curve, we only want that much area. In the green curve, notice how the green curve is very, very flat over here. The green curve, we want hardly any probability at all. The point is, the probability of finding a value in this region depends upon which curve you're dealing with and what the mean is and what the standard deviation is. Now, in order to find those areas, we're going to need to do something. One possibility is to take a whole bunch of calculus and find the surface area that way. We're not going to do that. The other option is let somebody else do the calculus, let them make a big table, and then we will learn how to use the table to find those areas. That's the option we're going to take. And so more on that here in just a minute.